There was no river to dam, no tunnel to seal, no conventional wall that could simply be lowered into the ground. The water was moving underground, through the soil itself. So Japan tried something extraordinary: freeze the soil and turn the ground into a barrier. On March 11, 2011, a massive earthquake and tsunami struck the Fukushima Daiichi nuclear power plant, disabling all electrical grids and emergency generators. With power lost, the cooling systems failed, causing severe core damage in Units 1, 2, and 3. To keep the melted fuel from overheating, operators had to continuously inject fresh water into the ruined reactors. At the same time, a second water source was constantly moving beneath the plant. Natural groundwater flowing downhill from the inland mountains was migrating directly toward the compromised, highly radioactive basements. Unlike visible rivers, rainfall runoff, or surface drainage, groundwater moves invisibly, filtering through connected spaces in soil, gravel, and fractured rock. How easily water passes through these underground layers is known as permeability. At Fukushima, gravity pulls this hidden flow downhill from the high inland mountains toward the Pacific, driving approximately 1,000 cubic meters of groundwater directly beneath the plant area every single day. Most of this volume passes safely around the facility. However, a significant portion of the flow, about 200 cubic meters, seeps directly into the reactor and turbine building basements through structural joints, pipe penetrations, and old utility pathways. Once inside, this clean water encounters highly radioactive areas, mixing with the core cooling water and instantly expanding the volume of highly toxic liquid. Each additional liter of this mixture increases the site's massive water management burden. To control this expanding threat, TEPCO's immediate objective was clear: keep the moving groundwater from ever coming into contact with these contaminated zones. Blocking this water with a standard concrete or steel cutoff wall would require digging deep trenches directly beside the damaged reactors. But the ground here is packed with turbine building foundations, high-voltage cables, water pipes, and concrete utility tunnels. Heavy excavation risks cutting active lines or cracking subterranean structures, which could create new pathways for radioactive leaks. Also, prolonged manual labor in these high radiation zones presents severe safety risks for cleanup crews. To bypass these physical hazards, Japanese planners chose to turn the Earth itself into the barrier. This approach avoids driving a rigid structure through the buried infrastructure. Instead, engineers planned a network of underground pipes along a route 1,500 meters long, encircling the reactors and reaching 30 meters down to the bedrock. By pumping a chilled liquid refrigerant through these pipes, the system continuously removes heat from the surrounding wet soil. This causes the water trapped in the volcanic ash and sand to freeze into solid cylinders of ice. Over time, these individual frozen zones expand outward until they merge, forming a continuous low permeability barrier. This thermal shield wraps precisely around existing obstacles without disturbing them, offering a non-invasive way to isolate the complex. Unlike permanent concrete, the ice wall is highly flexible. If plans change, operators can simply turn off the refrigeration to thaw the ground. Constructing this subterranean barrier requires a precise 7-stage engineering process. First, specialized crews drill vertical boreholes into the earth along a mapped perimeter. Inside these holes, technicians install coaxial freezing pipes. Next, the surface refrigeration plant circulates a liquid calcium chloride brine, chilled to approximately -30 degrees Celsius, through the pipe network. This extremely cold fluid continuously extracts heat from the surrounding saturated soil. As the thermal energy escapes, the water occupying the soil voids begins to freeze. This phase change binds the sand and volcanic ash into a solid soil ice composite, which sharply reduces hydraulic conductivity and stops water movement. Over several months, the individual frozen zones around each pipe expand outward until they merge, forming a single, continuous frozen boundary. To keep this barrier intact, the system must maintain continuous refrigeration, balancing the natural heat of the Earth. The physical scale of this operation is immense. The pipe network forms a 1,500-meter loop around Units 1 through 4, reaching 30 meters down to the bedrock. Once fully active, the system encloses approximately 70,000 cubic meters of frozen soil, a massive volume of earth rather than stored water, transformed into a solid protective shield around the damaged complex. Water levels inside the contaminated reactor buildings differ from the natural groundwater levels outside. This disparity generates hydraulic head, the combined force of water pressure and elevation that governs underground movement. Simply blocking this flow risks shifting the hydraulic gradient, which could push contaminated water through basement cracks or redirect clean groundwater into new, unwanted pathways. To manage this delicate pressure balance, the Nuclear Regulation Authority established a staged activation plan in early 2016. Following the completion of all piping equipment in February 2016, physical freezing began that March. Rather than an instant shutdown, engineers activated the barrier in gradual phases. Operators carefully monitored soil temperature, groundwater level, water movement, freezing progress, and possible bypass pathways to keep the water level differential within safe limits. This progressive section-by-section activation allowed engineers to track underground dynamics until the large-scale installation reached full completion in March 2018. Over this multi-year process, the subterranean flow was permanently reshaped. TEPCO assessments concluded the frozen barrier was partially effective, claiming it blocked approximately 95 metric tons of groundwater daily. Yet, independent experts and regulators, including a Nuclear Regulation Authority panel, questioned whether this produced a clear net reduction in total inflow. They noted that seasonal rains and underground sand lenses made maintaining freezing temperatures difficult, leaving persistent gaps in the barrier. Rather than a standalone cure, the ice wall operates as just one component in a 5-layer defensive system. Layer 1 limits water entry using the frozen boundary alongside an upstream bypass. Layer 2 extracts groundwater using a network of sub-drain wells. Layer 3 seals the shoreline with seaside barriers to block leaks. Layer 4 treats the captured, contaminated water using the Advanced Liquid Processing System, or ALPS. Lastly, Layer 5 manages the treated water in storage tanks prior to its eventual monitored release. The frozen earth is not a complete solution, but a temporary shield buying time for a decades-long cleanup. The barrier is an active thermal system rather than a passive structure. To block groundwater, refrigeration plants must constantly extract geological heat. This creates an energy paradox. Heat must keep being removed to resist the water, requiring constant electricity. A network of pumps, sensors, and controls monitors the system to detect localized warming or equipment faults. If electricity fails, the refrigeration stops, but the ice does not vanish immediately. Backup generators and batteries maintain the monitoring, while latent heat slows the transition from frozen to thawed soil. TEPCO estimates the wall can maintain its effectiveness for approximately 2 months. Yet, how long a kilometer-scale frozen wall can remain part of Fukushima's defense is an unresolved operational question. The Japanese government and the Ministry of Economy, Trade and Industry directed approximately 34.5 billion yen in public funding to construct the frozen barrier. This upfront capital remains distinct from the lifetime operating and maintenance costs borne by TEPCO. To evaluate this investment, budget holders weigh the initial construction expense against the potential long-term burden of unchecked groundwater. When water enters contaminated zones, it triggers a chain of ongoing expenses: treatment, storage tank expansion, monitoring, and eventual disposal. No simple cost-benefit calculation settles the question. The wall serves as a risk management measure to reduce a compounding liability. Artificial ground freezing is not a modern invention. Since the late 19th century, civil engineers have used subterranean refrigeration to stabilize wet soil and block groundwater during mining, tunneling, and deep foundation work. Typically, these setups are temporary, lasting only until workers complete excavation. Fukushima, however, transformed this temporary construction tool into a long-term containment barrier. While independent technical reviews confirmed that the refrigeration equipment and physical principles were thoroughly understood, the scale and duration were unprecedented. Engineers adapted a familiar civil engineering method to a high-consequence nuclear environment where the system must run continuously for decades. Today, the ice wall remains a temporary shield under constant life support. It demands continuous energy to keep the Earth frozen. As the cleanup drags on, we must ask, how long can an active system hold back nature? Share your thoughts in the comments.